In my previous video, we talked about random variables, and then we talked about discrete and continuous distributions. In particular, we talked about density function, cumulative distribution functions, and expected values. In this video, we will continue by looking at particular examples of discrete distributions and continuous distributions. For the discrete distributions, we will look at geometric, associated with Bernoulli trials. We will look at the binomial distribution, and we will look at the Poisson distribution. For the continuous distributions, we will look at the uniform distribution, the gamma distribution, the exponential distribution, and the chi-square distribution. Finally, we will look at the normal distribution, which you're already familiar with. That's the one where your bell curve and your grades are. A really quick review of continuous and distributions in general. First, we talked about random variables, and those are variables whose values are determined by chance, some chance process. The density function essentially answers the question, what's the probability that a random variable x takes the value little x? So for discrete distribution, this density function takes the form of a table or a formula. So when it's a formula, you can plug in a value little x, and then the p of x will return the probability. Or it might be a table, you just look it up. For continuous functions, because there is an infinite number of possible values for little x, the probability that little x takes on any one particular value is infinitesimally small. So what we ask is, what's the probability that our random variable x falls between a value a and b? And to answer that, we sum up all the probabilities that our probability density function, little f of x, gives us between a and b. So density function, again, answers the question, what's the probability x is equal to a value for discrete? For continuous, that random variable x is between two values, a and b. And density functions are denoted with a little f. For cumulative distribution functions, that's denoted with a capital F. That's the probability that a random variable x is less than or equal to little x, our value. And if you recall, we kind of think of walking along the real number line from negative infinity up to x, and we add up all the probability densities that we've accumulated from negative infinity to x. So this is our formula. We just sum up all the probability density we've gotten from negative infinity to x, or for continuous functions, we integrate negative infinity to x, and then t is our dummy variable of integration. Last, we talked about expected value, and what that is a weighted average of all the possible values of x, and it's weighted by the probability that our variable takes the value x. So it's the summation of x times probability of x, or in the continuous case, the integral of x times the probability of x. And that concludes our 2-minute summary. We are going to do a quick overview of the 3 discrete functions so that when we do our examples, we can look at each of these 3 and determine which best fits. After we've kind of gone through each of these, done a number of examples, we will come back and fine-tune our understanding of each distribution by looking at the density function as well as the cumulative distribution. We will start with the geometric function. Here is the density function and the cumulative distribution function. And the geometric distribution is associated with a Bernoulli trial. And a Bernoulli trial is sort of an experiment that you can determine as being successful or unsuccessful. So an example might be something like, did you find the treasure? And the answer is yes or no. We'll say that if you did find it, the answer is yes, that we'll consider that a success. If the answer is no, you did not find the treasure, we'll consider that not a success, a failure. Another example of a Bernoulli trial might be if you and a friend decide to base a decision on a coin flip, and you like the decision, you get to make the decision if it comes up heads. So in this case, the coin flip coming up heads would be considered a success for you. The coin flip coming up tails would be considered a failure for you. So there's a definite success, failure, yes, no component of this Bernoulli trial. and the probability of success for any one trial is equal to p. Our random variable x is going to be equal to the number of trials before the first success. So we're going to run a few trials until we finally get a success, and that will be x. The other thing about these Bernoulli trials is they are forgetful. What that means is if you do this coin flip once, and then you decide, okay, let's do best 2 out of the 3, the second coin flip, the probability of success, is totally independent of the first trial, of the first coin flip. Similarly, the third coin flip, if it comes to that, the probability of success is still p. It has nothing to do with the first 2 trials. It's totally independent of the first 2 trials. Here are the formulas for expected value and variance, as well as the moment generating function. Our next type of distribution is the binomial. Here is the formula for the density function. And the binomial is also associated with Bernoulli trials, but in this case, we're going to run n trials, so maybe n coin flips. And the probability of success is still p. What random variable x now is equal to is the number of successes in n trials. And here's the formulas for expected value and var x. The last discrete distribution we will look at is Poisson. So the Poisson process involves observing discrete events in a continuous interval of time, length, or space. And our random variable x is going to be the number of occurrences of events in the interval of length s. So an example of a Poisson process is that we might go outside for an hour and count the number of cars we see pass on the road in front of the house. So the discrete event is a car passing by. And we might set our time length to be 1 hour. And then we'll, again, x, we'll just count how many times we see a car go by. Another example involving space, maybe it's something like if I want to talk about someone's cleaning habits, I might say something like, okay, in this 10 square feet of space alone, I count 3 of your dirty socks. So the discrete event is the dirty sock being in the space. And then the interval of space is the 10 square feet. And then I said there were 3 socks in there, so that would be my x. The things that we have to compute the density function is we are given gamma, which is the average number of occurrences of events per unit measurement unit. And we're also given s, and s is the interval of length s. So if it were 1 hour when we were waiting for the cars, or 10 square feet of space when we were counting socks, dirty socks. And then here's the formula for expected value, and also a note that the Poisson is approximately the binomial distribution for large n. Our first example is here. Suppose microchips are manufactured in such a way that 1 in every 20 is defective in some way. Chips are examined one by one, and x, our random variable x, denotes the number of chips examined in order to find the first defective one. What is the probability at least 5 chips must be inspected to find a defect? The first thing we need to do is determine if this is geometric, binomial, and Poisson. And I'm going to start by eliminating Poisson, because Poisson processes generally involve looking over an interval of time or interval of space to find some occurrence of some event. So the occurrence of our event is something defective, but we aren't really waiting for 20 minutes or something and then looking to see if something is defective, and we're not looking over some room full of things and then saying how many are defective in that room full. What we are doing is examining the chips one by one and determining if they are good or if they're defective. So this is a Bernoulli trial. So each time we pick up a chip, if we say it's good, that's considered a success. If it's defective, well, actually in this case, since we're looking for a defective one, maybe we want to say if it's defective, that's a success. And if it's not defective, that's a failure. You can really write it either way. But for now, let's just say our success is finding a defective one. So now all we need to know is this geometric or binomial. So here we're looking at the number of chips examined to find the first effective one. So in binomial, we have a set of maybe 5 trials, and then we determine the number of successes in the trials. So this does not sound the same. It looks like here, something of x, number of trials before the first success. So the number of trials before we find a defective one. Now that we've determined this problem is geometric, I put the formulas for a geometric distribution here, and I have the problem written down here. And I put my notes here that our success in this case is a defective chip is found, which is a funny way of defining success, but that's what we're looking for, a defective chip. So our probability of success is 1 in 20, and then often we use Q here to denote the probability of failure, so that's 19 in 20. Our random variable x is the number of chips inspected before the first success, or in other words, a first defective chip is found. And what we want to know is the probability that x is greater than or equal to 5, because at least 5 chips must be inspected to find a defect. So this is the notes. I translated the things in our problem into these notes. I've written this out. Probability x is greater than or equal to 5 is the probability that x is equal to 5, 6, 7, and we go on to infinity. So obviously we're not really going to be calculating this because we can't calculate. I guess we could do some sort of infinite sum, but we're not going to do that. But I do want to show you what these probabilities look like. The probability that x is equal to 5 means we are going to have 4 failures before our first success. So that means, recall that the probability of getting a failure, a failure, a failure, a failure, and then a success, if they're independent events, means we're going to multiply. So we're going to multiply our 4 failures, that's 19 over 20 to the 4th, times our first success, 1 in 20. Here we have probability x is equal to 6. That's 5 failures, that's the 19 over 20 raised to the 5th, plus 1 success. The probability that x is equal to 7, again, is 6 failures plus 1 success. The easy way to do this is to do the 1 minus the probability that x is equal to 4, 3, 2, or 1. So I have probability f is equal to 4, that's 3 failures before the first success. Probability x is equal to 3 is 2 failures and then a success. Probability x is equal to 2 is 1 failure and then success. And probability the first one is a success is right here. And here's my final answer. I cleaned this up a little bit, eliminating that false start, and I put in how we arrived at our solution so I could make a little more room to point out one other thing. We could have also used the cumulative distribution function to solve this, and that would be 1 minus f4, the probability that x is less than or equal to 4. So that would be 1 minus, and in this case, this is q, the probability of failure, 4 failures. So the probability of failure raised to the 4th, and you see that we get the same number. And kind of on that graph, right, we have x equals 1, 2, 3, 4. So we take the 100% for our cumulative distribution, and we subtract out 4 and less. I have one more thing to illustrate the forgetfulness of this geometric problem. And so what I want to do is calculate the probability that x is greater than or equal to 20, given that x is greater than or equal to 16. In other words, what's the probability we'll have to search through 20 or more chips, given that we've already searched through 16 and haven't found a defective chip yet? If you recall from conditional probability, the probability of A given B is equal to the probability of A and B occurring divided by the probability of B. So here I have the probability x is greater than 20 and x is greater than or equal to 16 divided by probability x is greater than or equal to 16. This top, as you may have already noticed, simplifies to probability of x is greater than or equal to 20. To calculate these probabilities, I'm going to use the cumulative distribution function the same way I did over here for p of x is greater than or equal to 5, and I'm going to let that be 1 minus f of 19, and then my 1 minus f of 15. I plug it into my formula for the cumulative distribution. In other words, there's 1 minus And in this case, the probability of failures, and there's 19 failures. And there's 15 failures. So the answer I get by the time I do these calculations is 0.8145. And if you'll notice, that's the same thing as the probability of x being greater than or equal to 5. In other words, it's the same here, because if we're at if we're at 16, then we want to know what's the probability we need to wait 5 more. It's the same thing as waiting for this 5. So again, if you're at x equals 16 already, you've waited and you've seen 16 that are not defective, what's the probability you're going to have to go 16, 17, 18, 19, 20, another 5 before you get a defective one? It's the same thing as if you started and just waited and you wanted to know what's the probability I have to wait for at least 5. In other words, the fact that you've already seen 16 doesn't make it any more likely than if you had started at 0 and were just waiting to get to 5. And that's the forgetfulness property. Said another way, let's say you're at a roulette wheel and you're betting on red, and you see that the last 16 plays have been black. So the probability of the next one being red is the same as if there were no blacks already, unless of course there's something wrong with the wheel, in which case, I guess that, all bets are off if there's like some cheating going on. But that's the idea of the forgetfulness property. It doesn't matter that 16 have already occurred. The probability of waiting another 5 is the same as if you hadn't had any Bernoulli trials occur. Here in roulette, on a fair wheel, it doesn't matter that there's 16 blacks have occurred. The probability of getting a red on the next one is the same as if this had been all random or that you just started the day. This next example is the ability to detect spots on a radar decreases as their appearance becomes too rare. The probability of correctly identifying a signal is approximately 0.9 when 100 signals arrive in 30 minutes. But this probability drops to 0.5 when only 10 signals arrive over a 30-minute period. And the hypothesis is that the unstimulated minds tend to wander. So let X denote the number of radar signals properly identified in a 30-minute time period in which 10 signals arrive. What is the density function of X? What's the probability at most 7 signals will be identified correctly? So the important things here is that X is going to be the number of radar signals properly identified. So there's this idea of you can do something properly or you can't. That's kind of a success or failure kind of thing. And a 30-minute period in which 10 signals arrive. And so the 10 signals, that's where our probability of successfully identifying the signal is 0.5. So this is, what is this? Number of radar signals properly identified in which 10 signals arrive. So this is a binomial. It is a Bernoulli trial because the success is being able to properly identify the signal. And it is the number of properly identified signals in 10 trials. So that's Bernoulli. Remember, X here, if it were geometric, that's the number of trials before first success, but that's not what this is about. This is about having 10 signals arrive. How many did you identify? That's binomial. And this is kind of tricky because this problem, I think, is intentionally set up to look sort of like a Poisson, because Poisson, you're given this number of occurrences. Oh no, you're given this lambda. Lambda, is that lambda? Okay, average number of occurrence of the event per measurement. And this here where it says 10 signals arriving over a 30-minute period, it kind of might make you think, oh, Poisson, except in this case, what you're counting is it's not like the number of signals that arrive in a certain amount of time. It's the success of or failure of determining the signal. So again, for that reason, it's a Bernoulli trial, and it is a binomial. Here I've written down the key information that I'm going to be using. So success is a properly identified signal, and the probability of success is 0.5, which means the probability of failure is 0.5. X, our random variable, is equal to the number of successes in 10 trials, right? X is the number of radar signals properly identified in a 30-minute period in which 10 signals arrive. So number of successes in 10 trials. Then I use my density function. So f of x is equal to c of 10 choose x. So I just use this notation here. That means out of 10 signals, x are identified. And since we don't care what order, like that we identify the correct signals all in a row, or it doesn't matter how our failures and our successes, it doesn't matter what order they come in. So that's why it's a combination. And then here's my probability of x successes, and here's my probability of n minus x failures. Ooh, I didn't realize how close I am to my first question answered, so I just need to plug in my p of x and my q of x, and this is my density function. And then my last question, find the probability at most 7 signals will be identified correctly. In other words, the probability that x is less than or equal to 7, and that is exactly f of 7. And so what I can do is just sum up from 0 to 7 the probability density function. So this is my summation of my density function, and I just plug in x equals to 0, x equals 1, 2, 3, 4, 5, 6, and 7. Our next example is the white blood cell count of a healthy individual can average as low as 6,000 cubic millimeter of blood. To detect a white cell deficiency, a 0.001 cubic millimeter drop of blood is taken and the number of white cells, x, is found. So x is the number of cells that are found. How many white cells are expected in a healthy individual? So the first thing we need to determine is what kind of distribution we have. And x is equal to the number of white blood cells. So one, it's not geometric because this isn't about number of trials before for success. It's counting the number of white blood cells. So maybe for binomial, maybe Poisson, number of occurrences, events in an interval. But I'm going to tell you that if it's by Bernoulli trial, you have to have repeated trials, and then you're counting the number of successes. So here, it's not so much that you're counting successes. I mean, I guess maybe you could think, oh, if we have a good number of blood cells, maybe that could be considered a success. Okay, let's go with that. But the thing is let's say I'm trying to determine if you have enough white blood cells, and I take that little drop of blood and I look at it and it's like, oh, look, you do have enough white blood cells, but let's do that 9 more times and we'll count the number of successes. That really isn't what's going on. And you would probably say to me, no, that test said I was good, and you're not going to let me prick you 9 more times. And really, so that this Bernoulli trial thing, that's really not what's going on. It's more like you're looking for the number of occurrences of an event, and that's spotting the white cells in an interval of length s. And in this case, the interval is the drop of blood. So you think of like the interval as like a space that you're looking for white blood cells. Sort of in the same way I was looking for dirty socks in that room in my previous example. Here you're looking for white blood cells in this space here, in the space in the drop of blood. So Poisson it is. Next, I'm going to write down the relevant information I need for my Poisson distribution. I need gamma, the average number of occurrences, and per unit of measure. And so that's 6,000, because this is the average. It can be as low as 6,000, so that's what I have. And then I need to know my length of S and my interval length of S. So S here, as I said, is going to be the 0.001 cubic millimeters of blood. So K times S is equal to 6 by this formula. So F of X is equal to e to the minus k, so e to the minus 6, k to the x, so 6 to the x, over x factorial. I hadn't been copying the expected value formula up here with the other things, but for this one I snuck it up there because it asked how many white cells are expected. So that's the expected value, and the expected value of x is equal to k, which is equal to 6. So that was quick and easy with the formula. The last problem is to find if at most 2, is there evidence of a white cell deficiency? So in other words, if x is at most 2, so x is less than or equal to 2, is there evidence of a white cell deficiency? So we're going to look at the probability of that occurring. So the density, then we're going to sum from x equals 0 to x equals 2. So that's the sum of x equals 0 to 2 of e to the 6th, our density function, 6 to the x over x factorial. So I plug in 0 for x, 1 for x, and 2 for x. And I didn't do the calculation. But essentially the idea is if this number is sufficiently small, that means it's a rare thing. So it's probably a deficiency because you want numbers that are kind of more common. Almost by definition, if it's rare, then it's not normal. So if the number, the probability you get is something very small, that means it's probably not, there's probably a deficiency and it's not considered normal. So that was our review of discrete distributions. We did a geometric distribution, a binomial distribution, and a Poisson. Now we are ready to go through continuous distributions. The first one is a uniform distribution, and that's when everything in an interval is equally likely. So if the interval is from a to b, so the probability that x will fall somewhere in the interval a to b, then the density is equal to 1 over b minus a. The next type of continuous distribution is a gamma function, which has this kind of complicated density function. It has kind of this 3 parts here, this one and the x to the alpha minus 1 and e to the minus x over beta. And generally, though, what we will be given is an exponential, which is a gamma function with alpha equal to 1. So we have this more simple density function. Or we have a chi-square, and that is a gamma function with beta equal to 2. And so every now and then you will be given a gamma function, not exactly in this form, but there is something interesting about the gamma function. This gamma function here in your formula, and that is how it integrates. So here's the definition of the integral of this gamma function, which gets plugged in here. And this integral is equal to alpha minus 1 factorial, so it's actually a very, it reduces to something simple, and actually how it works is really interesting, but I do have a separate video for that in case you need to know about the gamma function. But most of our distributions, when we do these continuous distributions, tend to be exponential and chi-square. But it's not difficult once you see it once. So it might be worth taking a look. But from the gamma function, we have this formula for the expected value and var x, which applies both to exponential and chi-square because exponential and chi-square are, in fact, gamma functions. So the exponential function is a gamma function with alpha equals 1, and here is the probability density. And exponentials often arise in connection with Poisson processes. That's the one that we had just done for discrete, and that's where you're looking at an interval and you're counting the number of times something, you can find something or an event occurs in that interval. It's forgetful also. So according to this theorem, a Poisson process with parameter, this is lambda, we can let w equal the time of the first occurrence of the event. So w is exponential with beta equals 1 over lambda. So here's our formula. It tells us about lambda. That is the Poisson. This lambda is our Poisson parameter, and we can, with the Poisson process now, we have a probability of w being the time of the first occurrence. Chi-square is with gamma is beta is equal to 2. The probability density is complicated, so usually we use tables for that. Last, we have a normal distribution, which I'm going to take advantage of the fact you're familiar with this because this is how grades are distributed, often distributed. The density function for the normal curve you're familiar with depends on a particular mean and standard deviation. So the mean, mu, and sigma are plugged in. So once you have those, you can figure out your probability, your density function. The thing is this is difficult to work with. So often we want to work with a table, except that because there are an infinite number of means and standard deviations, then you can't create a table for every combination of every mean and standard deviation, because that would be an infinite number of tables. So what we end up doing is, once we take a problem and we have our mean and standard deviation, we put it into a form called standard normal. And then we have one table for the standard normal form. And then when we have a normal distribution, we look up our probabilities in our one table. There is also associated with the normal distribution a normal probability rule, which we will take a look at. And that's good for determining outliers or just knowing how expected a value is. And then this last extra topic, the Chebyshev inequality, is sort of like the normal probability rule, except it applies to any continuous distribution. So it's not as accurate as the normal probability rule, but that's because it can be used in any distribution, and so that's quite impressive that it can be done at all. This is an extra topic that I have a separate video for. It's actually quite a short video. It's interesting, but I didn't really want to put it into this video because this video is long enough. Our first example is uniform distribution, and we know this because they tell us it's uniformly distributed. So a random variable x is said to be uniformly distributed over an interval AB if its density is given by f of x is equal to 1 over BA, which is essentially the formula for density of a uniformly distributed variable, for x between a and b. Show that this is a density for a continuous random variable. To show that something is a density function, there are two things we need to show. First, we need to show that the density is always greater than or equal to 0. And then the second thing we need to show is if we integrate over all values between negative to infinity, then we're going to get that equal to 1. So these are two things you probably know, but I probably should have put this, I definitely should have put this on my overview sheet. So this is something for you to know, and you should probably put it in there. I'm actually going to sneak it in when I'm doing my video, so it'll magically appear. But anyway, the third thing about density functions is once you have a density function, you can define then the probability that x is between a and b as the integral from a to b f of x dx. So first, since we're given that x is between a and b is larger than a, we know that 1 over b minus a, the density function, where is that? Over here, given to us in our problem, is greater than or equal to 0, again, because b is larger than a. So part number 1 is shown. Part number 2, we want to integrate our density function from negative infinity to infinity. And in this case, our density function is 0 until we hit a, and then from a to b we have density, and then after b it's 0 again. So we really only need to integrate from a to b, again because it's 0 outside this, the density function is 0 outside this interval. So our integral is just going to be 0. So from a to b we're going to integrate 1 over b minus a dx. So when we integrate this, we're going to get b minus a over b minus a, which is equal to 1. So we've shown that it's a density function. The next thing we want to do is sketch the graph of the uniform density. So I have my graph here, and I should label my axis. This is my f of x, my density function. And I have a and b labeled arbitrarily on the x-axis. And I kind of put some scale markings, but I didn't put numbers, so it could be however long. But I kind of indicated that maybe the length between a and b is something like 3, or is, 3 of these units, which are arbitrary. So then the height should be 1 over b minus a, so that should be 1 over 3. So I tried to make my height approximately 1/3 the height. It's not exactly to scale, but more or less. After that, we have shade the area of the graph that represents probability of x is less than or equal to a plus b over 2. So a plus b over 2 is this halfway point here. So I've shaded all of this portion here. That represents the probability is x is less than a plus b over 2. And this part here to the left of a, that probability is all 0, which is why it's not shaded. And since this shaded portion represents half of where all the probability density is and it's uniform, that means the probability is equal to 1/2. And in fact, the shaded portion represents 1/2 of the total probability. The last question, let C, D, and EF be subintervals of A, B of equal length. So I have D minus C is equal to F minus E because they're of equal length. What is the relationship between the probability of X being between C and D and probability of X being between E and F? So they are equal because the intervals that they occupy are equal, and that's the idea of uniform distribution. Everything has the same probability density if we're talking about the same interval length. Our next example is of an exponential distribution, which I have moved the formulas over here. Some strains of paramecia produce a secret killer particle that will cause death to a sensitive individual if contact is made. All paramecia unable to produce a killer particle are sensitive. The mean number of killer particles emitted by a killer paramecium is 1 every 5 hours. In observing such a paramecium, what is the probability we must wait at most 4 hours before the first particle is emitted? It's kind of strange talking about paramecium in a math class. But anyway, to see that this is exponential, we do have this explanation that it's in connection with the Poisson process. So we're waiting over an interval of time or space or length for something to happen. And then the exponential is a Poisson process where we let our random variable equal the time of the first occurrence of the event. So here we're waiting for a paramecium to emit a killer particle, paramecium. And we have the average, which is our lambda. And then we want to know what's the probability we must wait at most 4 hours before the first particle is emitted. So this is about W, time of the first occurrence. And again, we have a Poisson process. We're waiting over an interval of time for some event to happen. And that event we're looking for is a killer particle. We have a lambda, which is the average number per hour, which we are given 1 in every 5 hours. And then last, it's not a Poisson process, but an exponential because we're waiting, our random variable is about the time the first occurrence occurs. And again, here, that's what we're asking. What's the probability we must wait at most 4 hours before the first particle is emitted? So first I parameterize everything for my Poisson process. I made my length, my interval length equal to 1 hour. And I could have done 5 hours, but I didn't want later, if we're talking about 4, I didn't want my limits of integration to be fractions. So I broke this down to 1 hour. But what that did mean is my lambda then has to become 1/5. And that, again, lambda was the average number of events in our S, in our time span. So you could have done this as lambda equals 1 and S equals 5, but you'll have to adjust all your other numbers for that. So this is how I did it. So beta is equal to, according to this theorem, 1 over lambda, which is equal to 5. And my f of x is given by this function here, 1 over beta, e to the minus x over b. Plugging in, I get 1 over 5, e to the minus x over 5. And now I'm set up to answer the last question. What is the probability we must wait at most 4 hours before the first particle is emitted? In other words, between 0 and 4 hours. So I integrate my function between 0 and 4, and then this is my final answer. This next problem involves the normal distribution. Let x denote the number of grams of hydrocarbons emitted by an auto per mile. Assuming that x is normally distributed with mean equals 1 gram and standard deviation equals 0.2 grams, find the probability that a randomly selected automobile would emit between 0.9 and 1.54 grams of hydrocarbon per mile. If you recall, we talked about the normal distribution is this formula here, where we have a mean and a standard deviation. But rather than calculating this, we often use tables. The problem is we can't have a separate table for every possible mean and standard deviation because that would be an infinite number of tables. So what we do is we use a standard normal approach. In other words, we put all measurements in terms of how many standard deviations that measurement is away from the mean. And then once we have this standard normal, there's one table that we use for the standard normal. So what does that mean in terms of this problem? That means we know we have the mean and we have the standard deviation. So these numbers here, these measurements here, need to be put in terms of standard deviations. In other words, we need to ask how many standard deviations away from the mean is 0.09 and 1.54. And there's first I worked on 0.9. So how many standard deviations are we away from the mean? Well, we are 0.1 grams from the mean because the mean is 1, and I have this negative sign because we're less than the mean. Then in terms of standard deviations, which is 0.25, we just divide this by 0.25. So we are 0.1, oops, that should have a negative, divided by 0.25 standard deviations from the mean. Similarly, I look at 1.54. So how many standard deviations are we away from the mean? Well, we're 0.54 grams away from the mean. Again, I just subtracted the mean from 1.54. And then I divide by the standard deviation. So we are a little more than 2 standard deviations away from the mean in the positive direction. I find these drawings really useful. I do the bell-shaped curve, I put the mean, u equals 1, I put my measurements 0.9, which I have converted to 0.4, standard deviations, that's a sigma, and a 1.54 is my measurement, and that's 2.1. And this is a sigma next to the 2.16, it's not a 0. I had to move some things around so that I could show you the table that I have. And you need to be careful because the table that you use might be different. So this picture shows me what this table is about. It gives me the probability. It's basically the cumulative distribution. Distribution, yeah. So if you have x equals to say 2.16, it gives you the probability that your random variable x is 2.16 or less. So again, it's the cumulative distribution up to x. There are many tables that instead will give you the distribution. If you look up 2.16, it'll give you the probability that your variable x is between negative 2.16 and 2.16, and the coloring, the shading will look like this on your graph. But that's not the case with my table, but you do want to know what your table means, otherwise you'll be looking up these numbers and interpreting them incorrectly. Anyway, so I'm looking up 2.16, and often that's called a z-score. So I look down here at z, and I'm looking for 2.16. I don't have exactly that number, but it's somewhere between 21 and 22, which is 0.9821 and 0.9861. And what that tells me is the probability from here, and I highlighted this part in the table blue, so it tells me that the probability from negative infinity up to 2.16 is somewhere around 0.98. Okay, so the probability I have something less than 2.16 is 98%. Now I look up my z-score of negative 0.4. Actually, I just get the, yeah, here it is, the negative 0.4. So the probability that I'm negative 0.4 standard deviations away from the mean is going to be about it is going to be 0.34. Actually, I'm going to say about because I'm not going to put in all the decimals. So from here to here, actually, I'm going to do this in green, which is why I highlighted in green. That probability is 0.34. If I want then to get the probability that I'm between the 0.9 and the 1.54, I'm going to subtract 0.34 from 0.98, just like when we normally work with cumulative distribution functions. So again, if you have a different type of table, it might be a different type of subtraction. Putting all this writing this all down. So the probability that my random variable x is between 0.9 and 1.54 is the same thing. That's my probability that I'm negative 0.4 standard deviations from the mean and less than or equal to 2.16 standard deviations from the mean. So I'm between these standard deviations from the mean. So I'm going to look up my 2.16, my cumulative distribution at 2.16 minus my cumulative distribution at negative 0.4. And I look that up as negative 0.8. Over here, I look this up as 0.34, and I get 0.64. So I have an approximately 64% chance of emitting between 0.9 and 1.54 grams of hydrocarbon per mile. And I'm also going to get rid of this drawing here because it is not pertinent to my problem, to the tables I have. Last thing we want to talk about for the standard normal is that we have this normal probability rule that says the probability that a measurement, our random variable x, is within one standard deviation of the mean is equal to 68%. So in other words, if this is our graph of possible values for x and the mean is here, 68% of our values are within one standard deviation of our mean, or 68%, of our probability mass is within one standard deviation of our mean. The probability that we're within two standard deviations is 95%. So if we go 2 standard deviations from our mean in this direction and also in this direction, 95% of our probability mass is in between these two. And then finally, if we go 3 standard deviations, we have 99% of our probability mass. So here within 3 standard deviations, we have 99% of our probability mass. So if you have a measurement that's outside 3 standard deviations, that's considered an outlier because it really is, 1% of our values will be outside 3 standard deviations. So this will give you kind of a measure of how unusual things are, or where you expect data to be. And then we have this really amazing Chebyshev inequality that gives us numbers like this, but for any distribution. It's not as accurate, but again, it's because it applies to any distribution. At this point, we've looked at the definition of a random variable, a variable whose value is determined by chance. We've talked about density functions, which gives us the probability that x takes on a certain value. We've talked about cumulative distribution, which is the probability x has a value less than or equal to little x. And we've talked about expected value. These things were covered in a previous video. In this video, we talked about discrete distributions, including geometric and binomial. Both of those depended on Bernoulli trials, where you would have a trial and you would be able to determine if something was a success or a failure. If we counted the number of trials before the first success, that was a geometric distribution. If we counted the number of successes in n trials, that was a binomial distribution. We also talked about the Poisson process, which was looking for an event, a discrete event, in some interval of time, length, or space. We talked about uniform distribution, when every value has the same probability of occurring over some interval, B to A or A to B. We talked about the gamma function. In particular, we talked about the exponential gamma function. And this arises when we have a Poisson process, and now our random variable is going to measure the time of the first occurrence of the event. We didn't go through chi-square. We did do the normal distribution, and we talked about how this is the formula for the normal distribution, but it is dependent on the mean and standard deviation, and because you can have many different means and standard deviation, we only have one table, and to use this table, we have to put things in standard normal form. That's when all measurements are put in terms of how many standard deviations the measurement is away from the mean. And we also talked about the normal probability rule that gave us an indication of how common things were. So the shape of a normal probability means 68% of our probability mass will be within 1 standard deviation, 95 will be within 2 standard deviation, and 99% of our probability mass will be within 3 standard deviation. So that's it for this video. Thank you for watching.